Hi, welcome to COMP501 Foundation of Programming. In this lecture, I'm going to talk about algorithm analysis. So, we have been writing a lot of program to solve problem, and students will turn in program that may look different. So when two programs solve the same problem but look different, is one program better than the other? This is always a question in a lot of people's mind, right? So when you say better, how do you determine which one is better? What are the criteria? Better in efficiency, computing resources like CPU or memory? What other way to measuring which one is better? Computing resources, um, there's a two computing resources usually when we compare the algorithm. One is how much memory the algorithm requires to solve the problem. The other is the amount of time the algorithm needed to solve the problem. This is the execution time or the running time. In practice, designing an efficient algorithm aims to lower the amount of time that an algorithm runs. What that means is it takes a shorter time to run the algorithm. You might be wondering, hey, most of my problem when I click the run, it return the answer right away. Well, that is true. What happens when the input size increases? If you have a list of 10 items, it returns quickly. What happens if a list of million or 10 million or billion items? How long would your program going to take to do the job? That is what the emphasis in this lecture here. So let's look at some of the operation, constant time operation. Um, Everything we've been doing, like a statement, when we do an if statement, when we do like an assignment statement, these are constant time operation. These operation, for the given processor, is always take about same amount of time to complete, regardless the input value. Whether you're doing like 100 times 100 or billion times billion, the time it takes for computer to calculate that is about the same time. And so anything that had to do with arithmetic, assignment statement with a fixed size data value comparison, like an if-else statement, or read and write an array value at a particular index, those are all constant time. It does not affect the size of the input data. When I say size, I don't mean the number is large. I mean number of inputs. Take a look at the linear search. We talked about linear search in um, last week when we talked about like a singly linked list. When you do a search item, you go from the beginning of the list to the end of the list and look for the item. If you find it, you return the node. If you don't, you return null, or in this case -1. Same with the Python code here. This linear search, I search the item from the beginning to the end, and if the number sub I equal to the key, I return the index. So given the list say 1, 5, 2, 10, if I'm looking for say 2, the index are 0, 1, 2, happen to be 2 here, 3. If I'm the index, if I'm my key, it will return the index. But what happens if I say I look for 20? It's not in this list, it will return -1 then. This is a linear search. Now when I say earlier, what happens if the list get bigger? This is a list of 4 elements. What happens if the list has 1000 elements in the list? What about if the list has 10 million items? What can happen to the search time? What do you think will happen to the search time? This operation, this statement, is a constant. So if I only have a 4 element, so the worst case would be it would take up to 4 comparison to find out whether the data I'm looking for is in the list or not. If it's 1,000, it would do up to 1,000. If a million, it would 10 million, it would do up to a 10 million to find out whether the item I'm looking for is in the list or not. So the algorithm runtime in the linear search, as you can see, depend on the size of the input. How many items in the list? If the comparison take 1 microsecond, then it will take up to 1 second to do 1 million and 10 seconds to do 10 million just for the comparison only. So as you can see, the time progressively get longer when the input size get bigger. And for a list of n elements, the linear search require at most n comparison. So you can say this algorithm require on the order of n comparison, and that is why it's called linear. It's proportional to the number of input. As opposed to binary search is like a guessing game, where the host will give you a hint on whether your guess is higher or lower. So if I say guess my number between 1 to 100, your logical guess would be 50, right? Because I will tell you higher. When I tell you higher, you know the number that I'm looking for is not between 1 to 49 or 1 to 50 in this case. You just eliminate half of the choices. If the number must be between 51 to 100 now. So your next guess might say, hey, 75. And I will give you another hint, lower. Now you just eliminate everything from 75 to 100. So every time you make a guess, and if the guess is wrong, you eliminate half the guess by checking whether the number is higher or lower than the guess. And this is how binary search works. In the binary search, we first check the middle element of the list. If the search is fine, great, and done. If not, then the algorithm repeat the search on the remaining left sublist if the search key was less than the middle, meaning the lower half, or remaining right sublist, meaning the upper half, if the search key is greater than the middle element. And this is the code how this works. I'm using a integer division to find the midpoint, the mid index. And I check if my number submit is less than the key, then I change my lower. The midpoint less than the key, the item must be in the upper half. So I change my lower to the mid plus 1. If number sub key greater than submit is greater than the key, then that means the midpoint value is greater than the key. The item must be in the lower half. I change the high to mid minus 1. So initially, think about this is my mid, this is my low, and I don't have a room here, so I put a high over here. If number submit, the number over here is less than the key, that means if I will change my low to here to search for the upper half. If number submit is greater than the key, that means I want to change my high now to over here to search for the lower half, keeping the low. This is by updating the low or high index, I can search for the lower half or the upper half. If it's not less than or greater than, it must be equal, so I return the mid. I found the key, I return the mid. And if the loop completed without returning an element, that means the item is not in the list. I return -1 for not found. Now, binary search is a very efficient algorithm. And the only thing about binary search is the list must be sorted. It just says when I say guess a number between 1 to 100, 1 to 100 is in sequence. So in order to use a binary search, the list must be sorted. And during the iteration or the step, the binary search reduces the search space by half and half and half. Eventually, you have one element, and you do the last comparison. If the element what you're looking for is the key, great, you find it. If not, the element is not in the list. For example, if the list has 32 elements, it would take 5 split. So um, 32 becomes 16, become 8, become 4, become 2, become 1. If we split one more time, it will become empty. So how do you get 5 from 32? Well, 2 to the 5th power is 32. Why 2 here? Because this is a binary. Binary means 2. Because you're cutting things in half. So the number of steps would be log of n to the base 2 plus 1. This will basically take 6 steps to get to 0. And this one here you can actually eliminate because this really shows you binary search proportional to log of n. If n is 1000, it will take you 10 split. If n is 1 million, it will only take you 20 split. If n is 1 billion, it will only take you 30 split. Imagine these number here. 1000, 10 split. 1 million, 20 split. 1 billion, 30 split. Imagine compare binary to the linear search. If I have 1 billion item in the list using linear search, that's a 1 billion comparison versus 30 comparison in binary search. You can see how the power of the binary search here. So you can use 2 to the some power must be greater than or equal to n. And to find this basically is a logarithm. Log n to the base 2 will give you how many split. So as I said earlier, if the comparison take 1 microsecond, a binary search would take at most 20 microseconds to search a list with 1 million, 21 microseconds to search a list with 2 million, and 22 microseconds to search a list of 4 million, and so forth. And this is a huge improvement over the linear search. But one thing you have to remember, in order to use a binary search, the data had to be sorted. And that is why searching and sorting are the two most studied algorithms in computer science.